Hello everybody, welcome to another video lesson. Today we are going to be looking at complex numbers in polar form. We're going to be able to convert them between rectangular and polar form and vice versa. All right, so let's hop into the concepts. A little review on our complex numbers. We must plot these on the complex plane, right? Also we call the Argand plane. Okay, Argand plane is how we say that. That's just our complex number plane. So if I have a complex number z, that is going to be expressed as a plus bi. Now remember, a is going to be the real part of that, and b is going to be the imaginary part of my number. That is a complex number that is composed of real and imaginary parts. So on a graph, this would look something like this, right? We have our real plane, that's going to be our horizontal plane, and now our vertical plane, or our vertical axis rather, is going to be our imaginary axis. So this point here, a plus bi, would have coordinates ab on the Argand plane. Now when we talk about the absolute value of a complex number, well, that is going to be the distance from the origin, okay, in the complex plane. Remember, the absolute value of any number, any real number, is just the distance from the origin or from zero on a number line, right? So it's similar for our complex numbers, it's just going to be the distance from the origin. So in order to find that would be this distance right here, right? This would be an absolute value. So in order to find the absolute value of z here, this distance, we would take the absolute value of a plus bi, which is just going to be using our Pythagorean theorem, right? We have square root of a squared plus b squared, because we can see here that we are dealing with a right triangle. So that is going to be the absolute value of a complex number, which is going to come in handy when we look at our polar coordinates in polar form. Okay, so let's look at converting these complex numbers into polar form. So we have our same setup here. We got a plus bi. Now cosine, you can see, of theta that we have here is going to be what? That's going to be a over r. And sine theta is going to be b over r. Right? So if I solve this for a and b, I get a is equal to r cosine theta, b is equal to r sine theta, which looks a lot like our x and y values, right, that we had when we were in the xy coordinate plane. So not much has changed here. We just have a and b now that we're solving for. So if I have my general complex number, z equals a plus bi, we can substitute in these values right here, right? Okay, so z is going to be r cosine theta plus r sine theta I. Now we can factor out an r here. And this right here is going to be our polar form of complex numbers. Okay, this is the polar form of complex numbers. So we can also abbreviate this, guys, in case you see this, r cis theta. This just stands for cosine imaginary sine. Notice here how I have cosine, imaginary, and sine. So if you see cis, that is just an abbreviation of the complex number in polar form. Okay, so we're going to use both of these formats here today so we can kind of get used to both of them. Now, what is r? R, again, is our absolute value. That's our distance from, this r should be up here, r. That is our distance from the pole to my imaginary point here, okay, or my imaginary complex number point. And we also call that the modulus. Okay, so if you are ever asked to find the modulus, you are finding the absolute value or the distance from the pole to that point. And we find that the exact same way as we found the absolute value of z, right? We just have a square root of a squared plus b squared. Nothing changes there. Now for our theta, in order to find theta, we would go ahead and use our tangent equation. And we would say theta is equal to the inverse tangent of b over a, which we have used before, right? Now keep in mind, because inverse tangent has a domain of negative pi over 2 to pi over 2, right? That is going to be quadrants 1 and 4. So if a is less than 0, that means we're in quadrants 2 or 3, so we need to take the inverse tangent of b over a, and then we need to add pi to it, and that's going to get us in the correct quadrants for our inverse tangent operation. All right, so that's our concepts. Let's go ahead and get into some examples. First things first, let's graph and then find the absolute values of some complex numbers in the complex plane. So we have our complex number 5 plus 2i. So we're going to move along the real coordinate axis. The real axis is going to go over 5, positive 5, and then we're going to go up 2 on our imaginary axis. Now we just plot our point here at the intersect of these two lengths, and we have coordinates of 5, 2 on our Argand plane. Now what we're asked to find here is its absolute value. Absolute value is going to be, again, this distance from 0, from the origin. So we find that by taking the square root of a squared plus b squared. So it's going to be the square root of 5 squared plus 2 squared, or the square root of 29, which is approximately 5.39. Okay, so you guys go ahead, pause the video, and graph and find the absolute value of a -3 plus 4i. All right, here's what I got. Hopefully you got an absolute value of 5, and your graph looks something like this. Okay, moving on, we're going to express our complex numbers in polar form. Now keep in mind, in polar form is different than the polar coordinates of a complex number. Those are two different things. So we're going to express this in polar form, which is going to be our r cis theta, right? Or z is equal to r cosine theta plus I sine theta. And then this is just the abbreviated version of what we have here. So let's find our r first. R is just the absolute value, which is going to be the square root of a squared plus b squared. So that's going to be square root of 9 squared plus 7 squared, or square root of 130, which is approximately 11.4. Now we just need to find our theta value, and we have a positive a value, so we don't need to add anything to this. We just need to take the inverse tangent of b over a. So that's going to be inverse tangent of 7 over 9, which is approximately 0.661 radians. Remember, we are doing this all in radians, guys. Do not do this in degrees. Okay, so our final polar form would just be r, which is going to be 11.4, cosine theta, which is 0.66, plus I sine of 0.66. Okay, so that would be our polar form. So now you guys go ahead and pause the video and find the polar form of -2, -2i. Okay, hopefully you got 2.83 cis 5 pi over 4. That would be our polar form there. And if you wrote this out the long way, that's fine as well. All right, last example here. We've got graphing and converting. We're going to graph our complex number on the polar grid now. Okay, we are not doing this on the complex plane. We are doing this on our polar grid. And then we're going to express it in rectangular form. So we're going to convert it back now into rectangular form. So here, let's think, what is my r value? Well, that's this value out here, right? So that's 5. And then what is my theta value? Well, that's going to be whatever I have inside my cosine and sine, right? So that's just going to be 3 pi over 4. So in order to graph that, that would be 3 pi over 4 is this reference degree right here, this reference angle. And then we would go out 5, right? 5 values. So that would put us right about there. So now in order to express this in rectangular form, let's just go ahead and think, well, what is the cosine of 3 pi over 4 and what's sine of 3 pi over 4? Well, knowing my unit circle values of -√2/2 and √2/2, we can just substitute those in to our values here, to our sine and cosine. So that's going to be 5 -√2/2 plus √2/2i. And from here, you can then distribute that 5 through, and we have our final complex number in rectangular form. It would look just like this. Okay, you guys go ahead now, pause the video and do the same thing here, graph this and then convert it to rectangular form. All right, hopefully your graph looks something like this and your rectangular form looks like 2 minus 2√3i. All right, guys, that was a quick one. That is all for our video today. Good luck with your practice.